Okay, George? In the range of our normal experience, the speed of a body is related to its kinetic energy like this. This Newtonian relationship applies even when we use speeds such as those of rocket travel or the speed of our Earth in its orbit about the Sun. We are going to use speeds that are very much higher than these and see if this relationship is still valid. As you can see, for the speeds that we're accustomed to, the velocity squared is proportional to the ratio of the kinetic energy to mass. Therefore, to get a very high speed for a given amount of energy, we should work with particles of small mass. We'll use electrons. Here, we have plotted this Newtonian relationship for electrons. This straight line represents velocity squared compared to kinetic energy. Because of the energies we have available in this laboratory, we have plotted kinetic energy along the horizontal axis in units of millions of electron volts. 1 electron volt is the energy gained by an electron going through a potential difference of 1 volt, or 1.6 times 10 to the minus 19 joules. The vertical axis represents the speed squared in units of 10 to the 16th meters squared per second squared. The square of the speed of light, for example, is here. 9 times 10 to the 16th meters squared per second squared. The square of twice the speed of light is here. According to the Newtonian prediction, when we use millions of electron volts, we may expect speeds way up here. These speeds are huge compared, say, to the speed of our Earth in its motion about the Sun, which we would have to plot way down here, completely invisible on this scale. To do these very high-speed experiments, we are working at the Linear Accelerator Laboratory at MIT, and this is the particular apparatus we're going to use. Here is the source of our electrons. They are boiled out of a hot cathode in a vacuum here. Incidentally, here is the belt of our Van de Graaff electrostatic generator. When this electrostatic generator is assembled and running, the potential difference across its terminals from here to here may be 1,000,000 volts. Because of this voltage, which is smoothly distributed by these planes, there is an electric field in this region that pushes on the electrons as they move from the electron gun at this end, where the hot cathode is located, through the holes in these planes to this end. When the electrons reach this end, they have acquired a kinetic energy equal to their charge times the voltage across the Van de Graaff. Then the electrons enter this evacuated metal coupling where there are no longer any electric fields. And because there are no electric fields, they just travel on without changing their speed. Before following the electrons further, let me point out to you that this electron gun is not on continuously. It is turned on periodically by this pulsar for a very short time interval. 3 times 10 to the minus 9 seconds. That is 3 millimicroseconds. This time period is short compared to any other time interval in our experiment. Thus we have many electrons in a bunch or a burst, and the whole burst moves together. We are going to measure the speed of such a burst. But since each electron in the burst has about the same energy, and thus the same speed, this is the same as measuring the speed of each individual electron. Let's follow a burst of electrons. It goes through this metal coupling here, always coasting freely, through this metal valve, which is open, past this shielding wall, and here it enters this metal pipe of the linear accelerator. Now, for most of the experiments we will do, the linear accelerator will not be turned on. All that complicated machinery there will be doing nothing at all. We will only use the long metal pipe inside here. It has nothing in it. It is free of air and of electric fields, and will make a good flight path for our burst of electrons which can coast freely down the whole length of the metal pipe. To find the speed of the electrons, we will measure the time it takes for the electrons to go from one end of the pipe to the other. Our first timing position will be here, where the electrons enter the pipe. We will measure the time it takes for a burst of electrons to travel from here, along this pipe, right down to here, through this 2-foot thick wall, into the target room, where it will end its flight by crashing into an aluminum disc. The distance between that aluminum disc and the start position is 8.4 meters. To do the timing, we'll make the electron burst give us a first signal when it passes the first position here, and another signal when it strikes the aluminum disc down there. To get the first signal, we have placed a short piece of metal tubing, like this, inside the pipe, here. The tubing is insulated from the pipe, so that when a burst of electrons passes through it, the electrons induce a charge on it that gives us an electric signal that comes out through this T connector and through the white cable below. This signal tells us when a burst of electrons passes by. This is our first signal. We will get our second signal from the aluminum disc that stops the electron burst in the target room. Let's go around and see it. Here we are in the target room. This is the pipe that we saw entering the other side of this 2-foot thick wall. The electrons come out here and enter this cup, which, when we do the experiment, will be attached here like so and evacuated. The electrons strike this aluminum disc, and we've made this disc thick enough so that none of the electrons will go through it. That means that every electron in the burst will stop in the disc. The disc is insulated from the rest of this metal cup, and the arrival of an electron burst at the disc will produce a signal which comes out here. Well, that's how we'll get our time of flight. One signal from the other end, and one signal from here. Now, when this apparatus is assembled and evacuated, we can get on with our experiment. The linear accelerator pipe has a good vacuum. The Van de Graaff is operating satisfactorily, and we're ready to send bursts of electrons down the pipe. We'll use this oscilloscope here as our timer. I'll turn it on. As you have seen, the oscilloscope is already connected to the start position by this short white cable, which carries a signal to trigger the sweep each time a burst of electrons starts down the pipe. I'll turn on the beam. You see the trace. We are using this oscilloscope at its fastest sweep speed. And at this setting, the spot which creates the trace moves across each of these large divisions in a little bit less than 10 to the minus 8 seconds. In fact, 0.98 times 10 to the minus 8 seconds. Now, to carry the signals from the beginning and end of the flight path to the oscilloscope, we'll use these two long cables here. We'll use this cable to carry the signal from the beginning of the flight path, and we'll use this cable to carry the signal from the end of the flight path. Now I'll turn off the beam, and I'll carry this cable to the start position. Here, I'll connect it to the short tube inside the pipe. Thus, it will carry our start signal to the oscilloscope. This is the signal that tells us when the burst of electrons starts down the long pipe. The signal comes along this cable, and here enters the oscilloscope. I'll switch on the beam. There, you see a signal showing up on the trace. Incidentally, our pulsar is firing the electron gun 120 times per second, so that there are 120 sweeps per second painting this picture on the scope face. The signal remains steady, however, because each burst is exactly the same as the one before. Now here is the other cable, the one that will carry our second signal from the aluminum disc in the target room when the electrons crash into it. These two cables have been carefully matched, so that if we start signals down these cables simultaneously, they will arrive at the oscilloscope simultaneously and appear as one signal on the scope face. Let me show you. I'll connect this second cable here with the first cable at the start position. You remember, the short white cable below carries the signal to trigger the sweep, while these longer matched cables will carry our timing signals. Now I'll turn the beam on again. You see one signal on the scope face. I'll disconnect this first cable. You see that the signal coming in through the second cable alone is in the same place as that from the first cable. I'll connect them both again. Once more, we have the larger signal. So signals starting down these cables simultaneously appear simultaneously on the scope. The cables are indeed matched. Now we'll shift the input end of this second cable, run it down to the other end of the linear accelerator through an opening in the thick shielding wall into the target room, and connect it to the aluminum target disc. And we know that the signal from the disc will start down this cable later and arrive at the oscilloscope later by just the time it takes for the burst to travel down the pipe. The connection is complete now. I'll turn the beam on again. Turn up the gain to see better. There are now two signals on the scope. As before, the left-hand signal is produced as the burst enters the pipe, and the new right-hand signal is produced when the burst is stopped by the disc at the end of its 8.4 meter flight. So, from the distance on the scope face between these two signals, we can calculate the time of flight and thus the speed. Let's do it. The separation, counting from the left-hand signal, is 1, 2, 3 large divisions, and 2/10, 3/10 of another. That is 3.3 divisions, a separation of 3.3 divisions. Now, to calculate the time of flight, we multiply this separation, 3.3 divisions, by the time it takes the spot making the trace on the scope to go one of these divisions. You remember that was 0.98 times 10 to the minus 8 seconds. And we get a little bit more than 3.2 times 10 to the minus 8 seconds. To calculate the speed, we must divide the distance of travel. You remember that was 8.4 meters by this time of flight. And we get about 2.6 times 10 to the 8th meters per second. I'll write that here. Speed in units of 10 to the 8th meters per second is 2.6. This is the speed of the electron burst when the voltage across the Van de Graaff reads 0.5 million volts. Therefore, we can say that the kinetic energy of each electron is 0.5 million electron volts. Let's plot this on our graph. First, I'll write it here. Kinetic energy in units of MeV is 0.5. I must square the speed. That's about 6.8. So the speed squared is about 6.8 times 10 to the 16th meters squared per second squared. At 0.5 MeV, this plots about here. Well, our result is way off the prediction of Newtonian mechanics. Let's try another run at a higher energy. I'll increase the voltage of the Van der Graaf to 1 million volts, double what it was. That means we're giving the electrons a kinetic energy of 1 million electron volts. The time of flight is less than before. Accurately enough, it is 3.1 divisions. The speed is about 2.8. in these units. The speed square is about 7.8. At 1 MeV, 7.8 times 10 to the 16th meters squared per second squared plots about here. This result is even further from the prediction of Newtonian mechanics. We need more data to see what's going on. We'll push the Van der Graaf up as high as we can make it go. It reads 1.5 million volts. The kinetic energy will now be 3 times what it was in our first run. This time, both pulses lie a little to the left of the large division lines. The right-hand pulse even more so than the left. So the separation is about 2.95 divisions. This makes our speed 2.9 times 10 to the 8th meters per second. 2.9 squared is about 8.4. At 1.5 MeV, 8.4 plots about here. This last increase in energy did not produce much of an increase in speed. Let's see what happens to the speed if we go to energies way out here. We can't push the Van der Graaf any higher, but we can get more energy by using part of the linear accelerator. We'll only use this first section here, 1 meter long. What we'll do is this. We'll keep the Van der Graaf set at 1.5 million volts, so that when the electrons in a burst arrive at this point, they already have a kinetic energy equal to 1.5 MeV. When the burst coasts into this piece of the accelerator, the section will turn on. The electrons in it will now be pushed on by the electric fields of a radio frequency wave generated by a power source over here and pass through waveguides into this section of the accelerator. When the electron burst comes out of this end of the section, the electrons will each have an energy of about 4.5 MeV. So, for about 1 meter of our timing run, that's up to here, the electrons travel with a speed corresponding to at least 1.5 MeV. From here on, for 7.4 meters, they travel with a speed corresponding to 4.5 MeV. That means, for most of its flight, the burst travels with a speed corresponding to its new energy. Now I'll go turn on the Linac. With the energy roughly tripled, we may expect an increase in speed and a shorter flight time. Let's go look. It looks as though the second pulse has moved in a little. The separation is 2.9 divisions, which gives us a speed a shade under 3. So, with the Van de Graaff in one section of the linear accelerator turned on, we have an energy of 4.5 MeV and a speed rounded off at 3.0. The speed squared plots over here a bit under 9. Even though we've tripled the energy, we've gotten only a very small change in speed. In fact, from the way this graph levels off, it looks as though there might be a limit to the speed that an electron can have, no matter how much we increase the energy. And from what we can see here, this limit might well be the speed of light, the square of which is 9 times 10 to the 16th meters squared per second squared. The way the speed levels off in our graph is contrary to our intuitive idea that if we push harder on electrons, they should move faster. We had better carefully check our experiment and see that we were indeed doing what we thought we were. Now, we needn't worry about our speed measurement. It was direct. That is, we measured the time it took for the electrons to go between 2 points a known distance apart. The distance divided by the time is the definition of speed. The other variable we think we were determining is energy. Here, we measured a potential difference, or electric field, in the Van de Graaff and in the linear accelerator. And from our knowledge that electric fields push on charges and transfer energy to them, we said that an electron going through a potential difference gained an amount of kinetic energy equal to its charge times that potential difference. But did that much energy really go into this motion of the electrons? We know that much energy would go into slowly moving electrons, but is it still true at these very high speeds? There are plenty of reasons to doubt. One possibility is that we really did transfer this kinetic energy to the electrons, but somehow the equipment rubbed it off during the flight. For any number of reasons, our reading of a voltage may not truly reflect the final kinetic energy of the electrons. And we must therefore make a direct measurement of energy to see that we are really adding as much energy as we think we are. And we're already set up to do it. Here is a second target cup fitted with an aluminum disc, just like the one in the target room. You will remember that we stopped the electrons by catching them in the aluminum disc. The electrons lose their kinetic energy in collisions with the aluminum atoms, and most of their energy goes into heating up the aluminum. So we can measure the energy in the bursts of electrons by finding out how hot the aluminum gets. And we can measure the energy per electron by measuring the charge and finding out how many electrons brought in that energy. Here, in the side of the disk, we have embedded a thermocouple to measure the change in temperature of the disk. These two wires from the thermocouple go out here to the connecting leads. The leads are plugged in here to the meter. You can see the meter is steady. But when I touch my hand to the disk with the thermocouple, the meter rises, because the heat from my hand raises the temperature of the disk and thermocouple. Each small unit of deflection of this meter has been calibrated to be equivalent to 0.8 joules of energy flowing into the disk. 0.8 joules to within 10% or better for measurements made in a time short compared to an hour. At the same time that we measure the heat, we can measure the charge flowing into the disk by allowing it to come out these terminals along a wire to the charge meter. This meter has already been connected to the cup in the target room, and it has been calibrated so that each click of its register is equivalent to 7.6 times 10 to the minus 8 coulombs. We'll set this duplicate target cup aside now. These leads are connected to the target cup installed in the target room. I'll connect them to the thermocouple meter. Thus, we will have both our meters tied directly to the target disk. Let's zero the meters. And before we start the experiment, we'll check the reading of the Van de Graaff. It is set to 1.5 million volts. I'll turn the beam on. The charge meter is clicking. Charge comes into the target disk, moves along the connecting wires, and accumulates on a capacitor in this charge meter. The rising needle shows the charge building up in the system. When 7.6 times 10 to the minus 8 coulombs has been collected, the capacitor is discharged. The register clicks over, and the needle flips back and starts to rise again. Thus, the register records the number of units of charge accumulated. Also, as the electrons crash into the target disk, they transfer energy to it, and the temperature of the disk begins to rise. You can see the indicator on the thermocouple meter beginning to shift away from 0 to the right. I'll read the thermocouple meter when the charge meter has made 80 clicks. This will take some time. $78, $79, $80. .5 divisions. So the energy carried into the disk is 12.5 times 0.8 joules. And the charge carried into the disk is 80 times 7.6 times 10 to the minus 8 coulombs. So, according to our thermal measurement, the energy per charge of the electrons is 12.5 times 0.8 divided by 80 times 7.6 times 10 to the minus 8 joules per coulomb. This is about 7.6 into 12.5, about 1.6 times 10 to the 6th joules per coulomb. Now, what did we think we had? According to the voltage reading of the Van de Graaff, the energy of the electrons was 1.5 times 10 to the 6th electron volts per electron. Since 1 volt is the same as a joule per coulomb, this is the same as 1.5 times 10 to the 6th joules per coulomb. And as close as we can measure, agrees with our direct thermal measurement. We'll leave the Van de Graaff at 1.5 million volts, and we'll turn on the first section of the Linac. we're all set. This is just like our last speed run where we thought we had 4.5 MeV. The meters are set to 0. I'll turn the beam on. Again, the charge meter is clicking. The charge is accumulating at about the same rate as before, but notice the thermocouple meter. It's moving considerably faster this time. Just as before, we'll read the thermocouple meter when the register on the charge meter reads 80. There. .36 1/2 divisions. Well, that's about 3 times the deflection of 12.5 divisions that we had in our 1.5 MeV run. For the same charge, we're feeding in about 3 times that energy. So in each of these runs, we were indeed feeding as much energy into the beam as we thought we were. And what's more important, we were getting it out at the target. The electrons really did have the energies we attributed to them when we measured their speeds. We've obtained by experiment, then, this result. As we increase the kinetic energy of the electrons from 0.5 MeV to 4.5 MeV, and we've measured this energy, the speed of the electrons appears to approach a limiting value. And as closely as we can measure, this limiting speed is the speed of light in vacuum, 3 times 10 to the 8th meters per second. Now, we have by no means exhausted our energy resources here. In fact, we often use this linear accelerator in experiments with nuclear reactions, which, if they're going to occur at all, require electron beams with energies of 15 million volts. So we can readily push our experiment one step further. As you recall, in our last speed measurement, where we used only this first section, the burst of electrons moved freely from this point on down the pipe with an energy of 4.5 million electron volts. Now we can turn on all these other sections of the LINAC. Then, as each electron goes from section to section, it will be pushed on again and again by the electric fields generated by these power sources. As the electrons come out of the last section of the LINAC, each will have an energy of about 15 million electron volts. This is more than 3 times the energy of our previous measurement. So, if there is any accompanying increase of the average speed over this flight path, we should see it. Each electron now has an energy of 15 MeV. What do you expect to see? The separation between the signals is about the same as in our 4.5 MeV run, 2.9 divisions. So the speed has not increased. You can see that our curve has indeed leveled off, since the last energy we used would be way out here. Clearly, the prediction of Newtonian mechanics does not explain this result. Early in this century, before high-speed data of this nature were available, it became evident that some improvement was needed in the theory because of other problems. Problems such as the relationship of Newtonian mechanics to electromagnetic phenomena. Einstein and others looked into the question of a better relation. According to the new mechanics they developed, the relativistic mechanics, the relation between v squared and kinetic energy for electrons is this. At very low speeds, this new curve and the Newtonian curve overlap as they should. At high speeds, this new curve also agrees very well with the facts we found. There is a speed limit for any object, and this limit is the speed of light.